Good afternoon, folks. Welcome to VCF. So, fantastic introduction. Thank you. I'm just going to start off with a quick poll. How many folks here have ever used a Commodore PET? A couple, okay. And how many have used a Commodore 64? Almost everybody. Okay. So, I've got material for both, but I'm going to be heavily leaning on the PET. So, it'll be educational for a lot of folks. As the introduction said, I got started with the Commodore PETs, doing things in BASIC first, and including building hardware. And then my first job ever was writing code for the Commodore 64. And my second job was more writing code for the Commodore 64, including sound effects, music, and so on. For that second job, the first thing I sold them was a background interrupt music player because we were doing kids' games, and they needed to be able to play nursery rhymes while the animation happened. So for folks that don't know the PET hardware, the basic PET is a 6502 with originally a 40 by 25 black and white screen, and the two tape interfaces, an IEEE 488 interface, and a user port. And what's missing from this is it makes no sound, the original ones. Later they added something, but the original PETs were silent, just like TRS-80s were silent, and the Apple II had just the single 1-bit beeper. So very early on, it was discovered, hey, you can use this pin. We'll go into some detail here on hooking up an amplifier to it, and you can make sound effects, but there's also a couple of other interesting ways to make sound on a PET that are not as common, but were still done back in the day. So my first introduction to sound on the PET was when we got Space Invaders, and when you first fired up Space Invaders, you got this splash screen before the game loaded showing you a picture of your PET and where to plug in this very simple circuit of a resistor to an output jack, and the, literally, this is the one I had back in the day. And we played a lot of Space Invaders on this. But beyond playing Space Invaders and having it beep, there's the exploration of, well, what else can we make it do? So it turns out this pin here that it's mentioning, the CB2 pin, happens to be, I found this recently, a different demo program also showed a similar thing, how to plug sound into your PET. So the 6522 VIA is a busy little chip. There's one 6522 in a Commodore PET, there's one in a VIC-20, and then it changed to the 6526 in the Commodore 64, for folks that know that better. They're similar, but not identical, so if you're used to doing any kind of I.O. or doing some low-level programming on the Commodore 64, some of this will look familiar. Importantly, there's two 8-bit I.O. ports, some handshake lines, and internally there's timers and many, many ways to control what's going on. The register listing of what all those are, you've got 16 registers in the 6522, which is the same for 6526. And again, many of the functions are similar. In particular with the PET, what you've got is port A is what's brought out to the user port, and also CB2, and then I think it's CA1 is the handshake line you get. And then internally, the PET is using the port B and the other handshaking lines for other functions. And on the back of the machine, this is somewhat different from what you're used to with the VIC-20 or Commodore 64, in that the bottom pins, A through N, are pretty close to the same. You have ground, handshaking lines, 8 bits of data, plus the top, in this case, you've got a bunch of weird signals that are not present on either the VIC-20 or the Commodore 64. One of the things missing is power. There's other signals that the 64 has that this doesn't, and vice versa. You can do composite video at the back of a PET using some of the pins here. But the important one is pin M there is CB2, and that's the pin we're going to focus on first. Whoops, that's actually not first. There is a different method of doing sound than CB2 on the Space Invaders, and that is to treat the entire 8-bit port as the source for a digital analog converter, and the software blows bytes out that get converted into sound. One of the vendors, this is a Petunia board. It's the two chips closest to the user port connector are just CMOS buffers, and what looks like two chips next to it are dip resistors. So this is doing a simple resistor ladder, and since I mentioned before, the PET does not have power on the user port, for PET accessories, they've got to tap over to the cassette port to grab power to power this circuit up. And the simple schematic where you have the input bits on the one side through the buffers into the resistor ladder. So as you program different bits in, they contribute different amounts. If you look at the very top, there's 4 lines that are all driving the same parallel resistance, and then 2 lines driving the same resistance through those dip chips, and then it's 1, and then it doubles and doubles again, and then it gets into discretes. So what you're doing is it's literally 1/4 of 47K, 1/2 of 47K, 47K, double, quadruple, times 8, times 16, times 32. So as you put different bytes in, each one of those lines is contributing more and more current into the output to sum all that up and give you the waveform. So you're doing, just like you would do synthesis on a modern sound card, this is doing it the hard way by punching bytes out of port and letting hardware give you different voltages in a very simple digital analog converter. And I'm going to try this. If we have sound on, which window is it in? Yes. So, for ease of use, and since I don't happen to own one of the Petunia boards, the Vice emulators happen to be able to emulate devices physically plugged onto the user port. And so this is the software you would get with the Petunia that lets you, that punches the bytes out. And I'm just going to play a quick sample to show how it goes. And this is, in real time, synthesizing waveforms to do multi-voice sound out an 8-bit port. And we're not getting it out the, here. Yeah. So I'm not sure how to convert this over. Should I try to move the mic?
If you want to, is that Windows?
It's not Windows, it's Fedora.
You set the audio device to the HDMI versus.
Okay. I have not. Yeah. I just haven't done it with this, and I'm.
Yeah, if you want to hand mic, I can do that.
Let's try that. There we go. So when you think back to the beep the Apple II makes, this is much more melodic. Petunias were around, I think, $40 back in the day, which was a bit of money, but still quite affordable. Eight-bit synthesis of audio at the user port. Generally speaking, with that, people did not roll their own. There's some great articles in Byte magazine by Hal Chamberlain, who is the founder of HUH, was the company. And so he wrote several articles on how to do this, and then several people made hardware, including his own company, MTU, that could do playback. But people didn't do a lot of sound hacking with this because it's pretty complicated, and there's a lot of math involved in getting the multi-layering of the sound going. So in the meantime, there we go. Another way to do this, also through the user port, it's a little faint. In April of 1979, in Byte magazine, Ciarcia Circuit Seller did an article on The Toy Story Begins at Home. And as he often had with his articles, he had a little saga where he went to the toy store at Christmas to buy a Simon, and the last one was sold out. So he said, well, that's fine. I'll just go home and make my own. And the article he published is this circuit, which I've redrawn, so it's a little more legible than the blue on white non-Xeroxing schematics they were doing for a while. Over on the far left side, there's were the connections to your whatever computer. He was using a CPM machine, but I built this circuit when I was a kid and hooked it up to a PET, and it works the same way, which is the PET can sense the 4 buttons that are on it, and the PET can also drive the 4 oscillators. So you've got 4 lights, and each of these circuits is its own independent oscillator, all run through the output speaker. And it happens to look like this. If you give me just a minute, I'm going to see if I can make it make some noise. I brought a PET, but because of time and setup, it was just easier to show this off in static mode than trying to run it from software. But the PET can poke bits into the user port and turn the audio on and off. This one I'll hold with the microphone because it makes noise out the speaker. Make sure I get this right. So very simple tones, nothing really magical, but before we had CB2 sound, this was one way to make sound on a PET, was by physically hooking up independent oscillators and controlling them through hardware. All right. I'm going to skip ahead here. Oh, where? What happened? I am missing a number of slides. What happened? That's unfortunate. I'm going to rotate back to CB2 sound here. I think something happened to my document. But in terms of the PET CB2 sound, so this is just one of several sample sound programs, and we're going to go over a little bit of how it's making the sounds after doing a quick little demonstration. Laser sounds, and this is all by talking through the CB2 bit. Okay, so what's going on here is I'm going to go back to the presentation for just a moment. the important parts, the feature we're taking advantage of with the 6522 is there is a register here. Register 10 is the shift register. And you can use it to literally just shift bits out the pin, like you want to convert parallel to serial. But there's a special mode. If you flip a particular bit in the auxiliary control register, it turns into free running mode, and it takes whatever byte you put in the shift register and just repeatedly shifts it out over and over and over again. And then you can use the low order timer 2, register 8, is what speed it will shift things out. So what you can do is you place a byte to be shifted, and then you can control the speed at which it's shifted. And routinely, this is all done with pokes. And in this case, this is the demo here giving you an example of what's going on. These are addresses of the different registers. So the top line here, this is the frequency in the timer control. The second one is the free running mode versus not free running mode. And finally, when they talk about waveform, this is the byte that gets shifted out. So what you can do is you can, let's see if I can pull this up. Wish this were larger, but here we are. If you punch in a number like 240 or 15, gives you the same results, which is half of the bits are on sequentially and then half of the bits are off. This will give you a square wave output on the CB2 pin at a particular speed, whatever the timer is set to. If you then change it to 204 or 51, which is 2 bits on, 2 bits off, 2 bits on, 2 bits off, you still get a square wave at twice the frequency. So you haven't changed the timer value, but because you've changed the bit value in the register, you get twice as many pulses per second, so that's 1 octave higher. And finally, if you use 170 or 85, that's 1 bit on, 1 bit off. So you get four clock ticks per cycle of the timer, so that's another octave higher. So you can play a variety of notes, and you can also vary these during playback, so that's how you get sound effects. Also, there's a certain tonality. This is a simple 1-to-1 duty cycle waveform, half on, half off. But if you place other values in there, then you'll get different timbres. You won't get quite a pure tone as we were hearing before, so we'll show how that goes. Let's cancel it. But that's what's all going into here where it says set CB2 waveform. That's controlling the byte that's going to get shifted out repeatedly. And there's a good note here. I found some references in some old newsletters going back as early as 1978 of people making reference to CB2 sound. And then suddenly in 1979, people said, oh, hey, by the way, you have to turn this off or it messes up the tape. And this became known later that you have to reset the free running bit or it does interfere with the kernel's tape routines. So this one is, I'll just play a couple of these. You can have it sound like a piano doing an up and down gliss. Or let's see, there's a random number generator behind this one. A little R2D2 noise. I think this one has a tone change to it. Yeah. That is not using one of the numbers I showed you before. That is not a simple 50-50 duty cycle. That's got an odd duty cycle, which gives it that almost not quite a sawtooth wave quality. Let's see. And what's another good one here? They're a little clever there. So just some basic sound effects. And fortunately, those are all written in BASIC. It's a little small. See if I can make this bigger. Thank you. There we go. Okay. So these are some examples. You heard some of these sounds. So this poke line, for example, that's setting that pure tone, that's the shift register value. You frequently, when you're going to look at programs where people have done these, you very often have just the raw numbers. If you're going to write programs, it's nice if you pick variables because you can see, oh, look, that's the shift register. Oh, that's the timer value. But routinely, you just see raw pokes in a lot of the sound effects programs. But here it's setting the value to be sent, and then here it's changing the frequency. First it's stepping up, and then it's stepping down. So you get that bits. And here, this x equals tan r has nothing to do with caring about the value. That's simply saying, go off and do some math and take some time. So it's basically a really cheap delay function. And let's see, they do some music here. Yeah. So their version of music is pretty crude, where it's literally poke into the frequency a particular speed for a particular note and do a manual delay loop. And by counting from 1 to 200 or 1 to 100, those are quarter notes or eighth notes if you're into music. And so it's literally poke a note, wait. Poke a note, wait. This is slow. I mean, it's hard to program, but for a sound effect program, it's not so bad. And again, same thing, this plays a little funeral dirge, and you can see it gets really tedious really fast. So one of the things people did is, let's get a different window up here. Here's some stuff that I wrote back in the day. Let's see. It's a short one. So that is more of a table-driven format. Excuse me. And what I did in this case was I used to have a piece of music notation paper with all of the frequencies written down so I could look at a note on the staff and go, oh, well, that one's 93. Oh, that one's 78. Oh, that one's 57. And then this is, again, that for loop timing delays to where it's quarters, eighths, half notes, and so on. And it's just simply read the data, and that gives you the value to poke into the register, and then how long to do your for loop for. So the other folks did things where you would store actual literal note names, A, B, C, D, put them into a data statement, and then convert those so that you're not typing and having to memorize what the numbers are. And it's just larger code. This has a 5-line playback routine. So that's pretty much the what's and whys and wherefores on we'll show this one's quick. Exit there, a little blinking. And for that one, I did just go ahead and poke the notes. It's 4 or 5 notes, so that was easier just to do that other simple sound effect level, do the pokes, do the delay, do the pokes, do the delay, and then do a little bit of star twinkling and blinking in between. So you can mix and match some of this music with a little bit of simple animation. So with that, I'm going to touch briefly on Commodore 64 sound, only really to delve into some of the stuff which may be familiar to folks. The SID itself is way more powerful than any of this. You know, we're talking about literally having control of 2 parameters for PET sound for CB2, where you can just control a very simple waveform control and a frequency control. In the Commodore 64, you have independent voices, so without resorting to any tricks, you can play 3 notes simultaneously very, very easily. And you also have full synthesizer control of the waveforms, where the register here, the 4th register in the playback, is you can control whether the source waveform is a square wave, a pulse, whether it's a sawtooth, where you've got a quick rise and a slow fall, and a quick rise and a slow fall, or triangle, slow rise, slow fall, or noise, where it sounds like static or crackling. And there's some other modifiers here, ring mod, sync gate, that let you do looping effects, and you can trigger on certain things, so when a threshold gets past a certain point. And these are full-on synthesizer features in the SID chip. And let's see, whoops. I was going to show off one of the programs. Got to figure out which window. Sorry, I've lost track of where I had that file. Sorry, I've lost track of it. What I've got here somewhere, sorry about that, is the program that I sold in 1984 that was the playback routine, and it's basically showing one way to talk to the SID chip, and how to keep track of instruments and do sound effects and do whistling. I can show the effects of it here. Take a minute to load. This is a commercial product written for the Commodore 64 back in 1984 for the place I worked at. It was sold through Reader's Digest, called Micro Mother Goose. One of my coworkers did ported his graphics routines over from the Apple, did the animation, and did all the sound. There we go. It's just taking its time to load. It was slower in real life, too. Randomly, I learned my first compression routine to write this, not to save space on the disk, but to let it load faster. There we go. So we had a composer-musician work at the company, and he came up with the score. I wrote a tool so he could input sound effects, do sweeps, create instruments. I think, yeah, it's loading. And this is playing in the background. One of the tricks you can do on PET or Commodore 64 is take advantage of the keyboard interrupt, which is a 60 hertz tick, and use that to do your timing. So the simple examples I was providing earlier are just using basic routines and statements to do the delays and synchronize when the sounds are going to happen. But for something like this, you can have an interrupt routine which gets automatically kicked off by the system 60 times a second, and use that to increment your own internal timers to know when to switch notes. And it's a particularly handy trick because you can do animation and music simultaneously. So I went through this a little faster than I intended. So with that, I guess if folks have questions, let me start there. If folks want to know anything in particular about creating sounds or working with the sound hardware in the machines? Oh, yeah.
Hello. Hey, so I'm not sure. So the original PET had no sound, and you used the cassette port or data port in the back of the PET. When Commodore implemented sound, is it the same?
So if you're thinking of the chirp noise that the later PETs made,
Like the little piezo speaker
right?
they put in there?
That is
Yeah.
totally on the CB2 pin.
Okay, so it is similar, I guess.
It's exactly the same.
Okay, that's all. That's my question.
Anybody else? In the back. Hang on, we got a mic coming.
So your example, the Twinkle Twinkle Little Star, I heard more than one voice. How did you program it to have polyphony?
So that's on the Commodore 64, which there are 3 voices in the SID chip. So the programming is literally the registers. You've got a complete set of registers for full attack, decay, sustain, release, waveform synthesizer independent of each other. So you can be quite complicated. Oh. If you have ever run any modern demos on Commodore 64s, you'll hear even more, because they will do tricks where, for instance, they'll take one of those 3 voices and they will interleave things like a rhythm track. So you hear percussion and you'll hear some other sounds because they're reusing one voice across time. But what we were doing there in 1984 was quite simple, and we just simply had 3 instruments and a musical score that literally had 3 parts. Anybody else? Questions? I'm at the end of my. Oh, here we got one in the front here. I'm just trying to use up a little more time because this went a lot faster than I had planned on.
Hello. Yeah, I was just wondering how widely adopted sound on the PET was in general, and was it mostly the CV2 technique that was used?
So for most games you're going to encounter, they would almost exclusively use CB2 sound. The DAC version of sound was usually self-contained. You would buy a board from a vendor, and they would provide software for their board, which they were kind of universal because everybody kind of copied from each other. So you could get a hub board and run Petunia software on it. It would sound the same. The hub board was a little more complicated, which is why I picked the Petunia for the example. It also included 3 levels of op-amp filtering and has quite a more complex circuit. That's the one Hal Chamberlain goes into great depth in his Byte articles on. And but ultimately, the software drove it the same way. The pins were assigned the same way, so it just sounded better, but it was the same general sense. So you would typically use one of their composers to write your own scores. It was a walled garden sort of a thing. You bought their hardware, bought their software, and that's all you could do with it is what their applications did for the DAC type software. But people who are writing all sorts of games almost exclusively use CB2. I brought along the Byte example because there is one other way you could do it, which is literally physically add hardware to the back of the machine that makes the noise.
Hi. Are those pet demos you were showing earlier, are those available readily?
Most of what some of the code I showed was code I wrote myself, but the fancier demos that I was showing off, those are typically available on places like zimmers.net.
Simmers. Oh, okay. Yeah, I've never looked at the pet stuff.
Yeah, there's in fact, I think there's a whole directory of, I grabbed several things from an audio directory. Some things are a little harder to find than others, but there's quite a lot of material out there on Zimmers, on making sound. And if you're used to using Vice, PetCat is fantastic for, just listing out and being able to tear apart what the programs are doing without seeing this much of it at a time.
Yeah, no, it's cool. I'm used to the 64 120 and stuff.
What about the VIC-20? Did they, was it in between?
It was in between. Thanks for bringing it up. I didn't include any material on it, but yes, the VIC-1 chip was both video and simple audio. As I recall, it was one voice, and it could do very simple, basically beeping and melody making, but not particularly complicated. Certainly not as rich a synthesizer as the SID chip. Any others? Okay, thank you very much.